Welcome everyone, and thank you for joining me today. I am Associate Professor Yasser Madany, a senior member of IEEE and URSI. Today, we'll be exploring the fascinating world of linear time invariant systems within digital signal processing. Over the course of this presentation, we'll cover key concepts, theories, and applications that are fundamental to understanding how these systems work. I'm excited to share this knowledge with you, so let's get started. Let's start with an overview of what we'll be covering today. We begin with an introduction to the fundamental concepts of LTI systems. Then, we'll dive into the analysis of continuous time LTI systems, which are systems that operate over a continuous range of time. Next, we'll explore discrete time LTI systems, where signals are sampled at specific time intervals. We'll discuss the key properties that define these systems, helping us understand their behavior better. Moving forward, we'll look at how LTI systems can be described using differential equations for continuous time cases and difference equations for discrete time cases. We'll also examine block diagram representations, which are useful for visualizing system components and their interactions. An important concept we'll cover is the eigenfunction of LTI systems, which relates to how certain signals are scaled but not altered in form when passing through the system. Finally, I'll go over the outline to give you a roadmap of our presentation, ensuring you see how all these topics connect to give us a comprehensive understanding of LTI systems. Linearity and time invariance play a crucial role in signal and system analysis for two major reasons. First, many physical systems naturally exhibit these properties, which means we can model them as LTI systems. This simplifies analysis and understanding significantly. Second, because LTI systems have the superposition property, if we can express an input or excitation as a combination of basic signals, we can easily determine the system's response. Essentially, we break down complex signals into simpler parts, analyze how the system responds to each part, and then combine those responses to find the overall output. This approach makes analyzing and designing systems much more manageable and connects directly to the core theme of understanding system behavior through fundamental principles. Let's take a closer look at the impulse response, which is a fundamental concept when analyzing continuous time LTI systems. The impulse response essentially tells us how a system reacts to a very brief input, an impulse, which is idealized as a delta function. By studying this response, we gain valuable insight into the system's behavior. It's like giving the system a quick tap and observing how it responds over time. This response completely characterizes the system, meaning we can predict how it will behave with any input by understanding its impulse response. This is key because it links directly to the overall theme of system analysis, understanding and predicting system behavior through fundamental responses. So, grasping the impulse response helps us analyze, design, and control systems more effectively in continuous time settings. Let's take a closer look at the convolution integral, which is fundamental to analyzing continuous time LTI systems. Essentially, this integral allows us to understand how an input signal is transformed by the system. The key idea here is that the output can be expressed as the convolution of the input signal with the system's impulse response. This means we're essentially sliding the impulse response across the input, weighting it by the input's values at different times. It's a powerful way to analyze systems because it captures the entire effect of the system's dynamics on the input signal. Connecting this to our overall theme, understanding convolution helps us predict system behavior and design systems more effectively. So, grasping the convolution integral is crucial for mastering how continuous time LTI systems respond to various inputs. Let's now focus on the step response, which is a fundamental concept when analyzing continuous time LTI systems. When we talk about the step response, we're essentially looking at how the system reacts over time when a step input is applied. This helps us understand the system's behavior in a real-world scenario, such as how quickly it responds and whether it stabilizes. It's important to recognize that the step response is closely related to the system's impulse response, but it provides a more practical perspective since step inputs are common in many applications. By examining the step response, we can determine key characteristics like the rise time, settling time, and steady-state value. This analysis gives us valuable insights into the stability and performance of the system. It helps us predict how the system will behave under different conditions. Overall, understanding the step response is essential for designing and controlling systems effectively, tying back to our broader goal of mastering system analysis. Now, let's look at an example of a solution in action. On this slide, we're focusing on one specific case to illustrate how our approach can be applied effectively. When we talk about this example, I want you to pay attention to the key points I highlight because they demonstrate the core concepts we've been discussing. This example helps connect the dots between theory and practice, showing how these solutions can actually work in real-world scenarios. Remember, the most important takeaway here is how this approach addresses the challenge we identified earlier and moves us closer to our overall goal. So, let's walk through this example together and see how the pieces fit. Now, moving on with our solution, let's delve deeper into some additional strategies. One key point to emphasize is the importance of customizing solutions to fit specific organizational needs. No one-size-fits-all approach works here, so tailoring your methods can lead to much better results. Another crucial aspect is ongoing evaluation and adjustment. Solutions shouldn't be static. They need to evolve based on feedback and changing circumstances. This keeps the implementation effective and aligned with your overall goals. Finally, I want to highlight how these solutions tie back to our main theme, creating sustainable, scalable improvements. When we approach problems with flexibility and continuous improvement in mind, we're setting the stage for long-term success. Remember, the goal is not just to fix issues temporarily, but to build resilient systems that support growth over time. Now, let's look at an example to illustrate this solution. This example helps us see how the concepts we've discussed can be applied in a real-world scenario. By walking through this, I hope you gain a clearer understanding of how the solution works in practice. It's a concrete way to connect the theory to actual application, which is crucial for grasping the full picture. So, as we go through this example, keep in mind how these key points come together to address the challenge we've been exploring. Let's talk about the impulse response, or what we also call the unit sample response. This is a fundamental concept when analyzing discrete-time LTI systems. Essentially, the impulse response characterizes how a system reacts to a very specific input, an impulse, which is like a sudden, brief nudge. By examining this response, we can understand the system's behavior in detail. It's important because, for LTI systems, the impulse response completely determines how any input will be transformed. Think of it as the system's fingerprint. Once we know this response, we can predict how the system will handle complex signals by convolving the input with this impulse response. This is a central idea because it links directly to the core theme of system analysis, understanding and predicting system behavior. When we analyze the impulse response thoroughly, we gain powerful insights into the system's stability, frequency response, and overall performance. So, in summary, the impulse response is our key tool for dissecting and understanding discrete-time LTI systems, connecting the dots between simple responses and complex behaviors. Let's take a closer look at the convolution sum, which is a fundamental concept when analyzing discrete-time LTI systems. Essentially, the convolution sum allows us to determine the output of a system based on its input and its impulse response. It's like a blending process. Each input sample interacts with the system's response over time, and by summing these interactions, we get the overall output. This process highlights how the system's behavior is shaped by its properties and the input signal. Understanding convolution is key because it provides a systematic way to analyze and predict system responses, which ties back into our overall goal of understanding how discrete-time LTI systems behave and are characterized. Let's take a closer look at the convolution sum, which is a fundamental concept in analyzing discrete-time LTI systems. Essentially, The convolution sum allows us to determine the output of a system based on its input and its impulse response. It's like a way of blending the input signal with the system's characteristics. When we perform this sum, we're effectively summing the products of shifted versions of the impulse response and the input signal. This process highlights the linear and time-invariant nature of these systems, meaning the output depends linearly on the input and doesn't change over time. Understanding this convolution sum is crucial because it forms the backbone for analyzing and designing many digital signal processing systems. It connects directly to the overall theme of analyzing system behavior, helping us predict how a system will respond to any given input. Let's take a closer look at the concept of step response in the context of analyzing discrete-time LTI systems. The step response essentially tells us how the system reacts when we apply a step input, which is a signal that switches from 0 to 1 at a specific point in time. By examining this, we gain valuable insights into the system's stability and dynamic behavior. It's important to understand that the step response reflects the combined effects of the system's poles and zeros, giving us a window into how the system will behave under real-world conditions. When we analyze the step response, we're really looking at how quickly the system reaches its steady state and how it handles sudden changes. This analysis is crucial because it connects directly to the overall theme of system behavior and stability. By understanding how a system responds to a step input, we can predict how it will react to other signals, which is fundamental in designing and controlling systems effectively. So, in essence, the step response acts as a practical tool to evaluate and ensure the desired performance of discrete-time LTI systems. Now, let's look at an example that illustrates the solution in action. This is example 3, which helps us see how the concepts we've discussed can be applied practically. As we go through this, I want you to focus on how the solution addresses the specific challenges we identified earlier. Notice the key points, such as the approach taken and the outcomes achieved. This example reinforces the overall theme of the presentation, that effective solutions are tailored, strategic, and adaptable. By understanding this example, you'll get a clearer picture of how to implement similar strategies in your own context. When we look at systems, their behavior can depend on different factors. Some systems rely on the value of past or future inputs, or even past outputs combined with the present input. These are called systems with memory or dynamic systems. They essentially remember what happened before and use that information to determine the current output. On the other hand, there are systems whose output depends only on the current input alone. These are known as instantaneous or memoryless systems. They don't keep track of past inputs or outputs, and their response is immediate based solely on what's happening right now. Additionally, we often classify these systems as linear time invariant or LTI systems. These systems can either have memory or be memoryless. Understanding whether a system has memory or not is crucial because it influences how we analyze and design them. Now, when we talk about the properties of LTI systems, there are some key points to remember. These properties help us understand their behavior, stability, and response characteristics. Recognizing whether an LTI system has memory or not, and whether it's dynamic or instantaneous, is fundamental to applying the right analysis techniques and ensuring system performance aligns with our needs. Let's take a closer look at causality in systems. It all depends on the value of the future input. If the output relies only on present and past inputs, we call that a causal or non-anticipative system. Essentially, these systems don't need to know what's coming next. They react based on what has already happened. On the other hand, if the output depends on future inputs as well, we refer to that as a non-causal or anticipate system. These are more theoretical in nature, often used in analysis rather than real-time applications. Now, when we talk about causality in LTI systems, linear time invariant systems, it's a fundamental property. Causality ensures that the system's output at any time depends only on the current and past inputs, not future ones. This is crucial because it aligns with how real-world systems operate. Understanding these properties helps us design and analyze systems more effectively. Causality is a key aspect because it impacts system stability, implementation, and how we interpret system behavior overall. So, grasping whether a system is causal or non-causal gives us insight into its practical applicability and theoretical foundations. Let's now focus on the stability of LTI systems. Stability is a fundamental concept because it tells us whether the system's output will remain bounded when the input is bounded. In simple terms, if you give the system a finite input, a stable system ensures that the output won't blow up to infinity. Next, we'll explore the invertibility of LTI systems. Invertibility is about whether we can uniquely recover the input from the output. This property is crucial when we want to reverse the effects of a system, such as in filtering or signal recovery. An invertible system means there's a precise way to get back to the original signal. Moving on, we'll discuss some important properties of LTI systems. These properties include linearity, time invariance, causality, and stability, among others. Understanding these properties helps us characterize the behavior of systems and predict how they respond to different inputs. Throughout this presentation, keeping these concepts in mind will help us see how LTI systems form the backbone of signal processing and communication systems. They provide a consistent framework to analyze and design systems efficiently. Let's take a closer look at some fundamental properties that are really important in system analysis. First, we have the distributive property. This property is all about how multiplication interacts with addition or subtraction. Essentially, it allows us to distribute a factor across terms inside parentheses, which simplifies complex expressions and makes calculations more manageable. Next, the commutative property comes into play. This one tells us that, for certain operations like addition and multiplication, the order of the numbers doesn't affect the result. So, whether you switch the order of the terms, the outcome stays the same. This property is quite handy when rearranging equations to simplify our work. Finally, we're looking at the properties of LTI systems, linear time invariant systems. These properties are crucial because they underpin how signals are processed in a predictable and consistent way. For example, linearity means that the system's response to a sum of inputs is the sum of the responses to each input individually. Time invariance implies that the system's characteristics do not change over time, so the output for a given input remains the same regardless of when it is applied. Connecting all of this to our overall theme, understanding these properties helps us analyze and design systems more effectively. They give us the mathematical tools and foundational principles to predict system behavior and ensure stability and performance. Let's take a closer look at the associative property, which is a fundamental concept when working with properties of LTI systems. The associative property essentially states that when performing operations like addition or multiplication, the way in which we group the elements doesn't change the outcome. For example, whether we group certain signals or system responses together first, the result remains the same. This is important because it provides us with flexibility in how we analyze and simplify complex systems. It also helps us understand that the order of grouping in operations doesn't affect the overall behavior of LTI systems. Recognizing this property allows us to manipulate signals and systems more efficiently, which ties into the broader theme of simplifying analysis and designing more effective systems. Let's take a closer look at the concept of a linear constant coefficient differential equation. This type of equation is fundamental in describing many physical systems. When we say it's a linear constant coefficient differential equation, we're emphasizing that the equation involves derivatives of the system's output, and the coefficients are constants, which simplifies analysis significantly. Now, when we describe an LTI system, or linear time invariant system, we're referring to systems that are both linear and do not change over time. These systems can be characterized using differential equations in continuous time or difference equations in discrete time. In this slide, we're highlighting that such systems can be described equivalently by differential equations or difference equations, depending on whether we're working in continuous or discrete domains. This dual description is powerful because it allows us to analyze and design systems using the most convenient mathematical tools for each case. Overall, understanding how these equations represent LTI systems is key to mastering system analysis and signal processing, which are central themes in our presentation. They provide the mathematical foundation for predicting system behavior, designing controllers, and analyzing stability. Today, we're going to focus on the concept of a linear constant coefficient difference equation. This is a fundamental idea when analyzing discrete time systems, especially those that are linear and time invariant. These equations help us describe how the current output of a system relates to its past outputs and inputs, which is crucial for understanding system behavior. We also see that an LTI system can be described by both differential equations and difference equations. Differential equations are used for continuous time systems, while difference equations are their discrete time counterparts. This duality allows us to analyze systems in different contexts, depending on whether our signals are continuous or discrete. The key takeaway here is that difference equations with constant coefficients are powerful tools because they simplify the analysis. They enable us to predict system responses and design appropriate controls or filters. Recognizing these equations as a bridge between continuous and discrete analysis helps us better understand the overall system behavior in various scenarios. Let's take a look at solution. Example 4. Here, we're exploring a specific instance that illustrates how our approach can be applied effectively. This example helps to clarify the concepts we've discussed so far and demonstrates how the solution works in a real-world context. By examining this example in detail, we can better understand the practical steps involved and see how the key points come together to address the problem at hand. Remember, the goal is to connect these ideas to the overall theme of improving processes and achieving better outcomes. Let's continue exploring the solution. On this slide, I want to emphasize that addressing these challenges requires a comprehensive approach. We need to look at not just the technical aspects, but also the human factors involved. For example, fostering collaboration across teams is crucial for implementing these solutions effectively. Another key point is the importance of adaptability. As the landscape evolves, our strategies must be flexible enough to keep up with changing demands. This ensures that our solutions remain relevant and impactful over time. Finally, connecting these points back to our overall theme, it's clear that a thoughtful, integrated approach is essential for achieving long-term success. By focusing on these core principles, we can overcome obstacles and drive meaningful progress. Let's take a closer look at block diagram representations. These diagrams are essential tools for visualizing complex systems in a simplified way. They use standardized symbols and connections to show how different components interact within a system. By breaking down a system into blocks, we can better understand its structure and functionality. This approach is particularly useful when designing or troubleshooting systems, as it highlights the flow of information or signals. Throughout this presentation, we've emphasized the importance of clear visual communication, and block diagrams serve as a perfect example of that. They help us see the big picture while also allowing us to zoom in on specific parts when needed. So, understanding how to interpret and create these diagrams is a key skill in systems engineering and design. Let's take a closer look at solution. Example 5. Here, I want to emphasize how practical examples like this can really bring the concepts to life. This particular example illustrates the key points we've discussed earlier, showing how the solution can be applied in real-world scenarios. It's important to highlight that these examples serve as a bridge between theory and practice, making the ideas more tangible and easier to understand. By connecting this example back to our overall theme, we can see how effective solutions are not just abstract ideas, but actionable steps we can implement. So, keep in mind that real-world examples like this are essential for grasping the full potential of the solutions we're exploring. Let's take a closer look at the eigenfunction of LTI systems. Essentially, eigenfunctions are special signals that, when passed through an LTI system, simply get scaled by a constant factor called the eigenvalue without changing their form. This is a critical concept because it helps us understand the fundamental behavior of these systems. The beauty of eigenfunctions is that they serve as the building blocks for analyzing complex signals and system responses. By knowing how an LTI system acts on these eigenfunctions, we can predict its response to more complicated inputs by decomposing those inputs into these basic components. This idea ties into the overall theme of system analysis and signal processing, emphasizing the power of eigenfunctions in simplifying what might otherwise be very complex problems. Let's now explore the concept of eigenfunctions of LTI systems. These are special functions that, when input into an LTI system, produce an output that is simply scaled but not changed in form. In other words, the eigenfunction is like a fundamental mode of the system. The importance of these functions lies in their ability to simplify the analysis of complex systems. By understanding how these specific functions behave, we gain insight into the system's overall response. This idea connects directly to our broader theme of system analysis, because eigenfunctions help us decompose signals into basic components. This decomposition makes it much easier to predict and analyze system behavior. So, recognizing these eigenfunctions is a powerful tool in our signal processing and systems analysis toolkit. Today, I want to focus on the concept of eigenfunctions of LTI systems. These are fundamental because they help us understand how systems respond to different inputs. The key idea is that eigenfunctions are special signals that, when passed through an LTI system, are only scaled by a constant factor, called an eigenvalue, rather than being altered in shape. This means that the system's response to these signals is very predictable and simple. Recognizing these functions allows us to analyze systems more easily and connect the dots between system behavior and signal properties. Overall, understanding eigenfunctions is crucial because they form the backbone for analyzing and designing LTI systems efficiently. Now, let's look at an example to illustrate this solution. As you can see here, we have example 6. This example helps us understand how the solution can be applied in a practical context. It highlights the key points we've discussed earlier, showing how the concepts come together in real-world scenarios. By examining this example, we can better grasp the effectiveness of the solution and its potential impact. Remember, the goal is to connect these points back to our overall theme of improving processes and achieving better outcomes. This example serves as a concrete illustration of how the solution works in action. Now, let's continue exploring the solution. On this slide, I want to emphasize that implementing these strategies is essential for achieving our overall goals. First, it's important to recognize that these key points build on what we've discussed so far, reinforcing how each element contributes to a cohesive approach. By focusing on these solutions, we're addressing the core challenges head-on and creating a pathway towards sustainable success. Remember, the most impactful part is understanding how these concepts interconnect and support our broader objectives. As we move forward, keep in mind that applying these insights thoughtfully will make a real difference. So, let's consider how each piece fits into the bigger picture and how we can leverage them to drive meaningful change. Thank you for your attention. If you'd like to get in touch or have any questions, here are my contact details. You can reach me via email at contact@Madany.com or Dr. Yasser, madany@yahoo.com. For professional connections, my IEEE email is imadany@IEEE.org. And of course, you can visit my website at https://imadany.com for more information and resources. Once again, thank you very much for your time and interest.